Ma'am.
Hi everyone, am I audible?
Yes, ma'am, you're audible.
So let's wait till 4 5 p.m. right? Because we changed the schedule last minute, so more people might be joining. So wait for 2 more minutes, then we'll start. So today is the week 9 session.
Madam, can you discuss means the format of OPP?
OPP, yeah, okay. So for OP, you will have 7 questions from SQL part, right? So you'll have 3 easy level questions, 3 medium level questions, and 1 difficult level question. And other than that, you will have 2 questions from Python DB connectivity part, that is from week 7. So out of those two, you have to do 1 question mandatorily. So that Python DB question, if you don't do, then it will be considered as fail, right? So at least do any one of them. And baki, the other is SQL questions, you have to score above 40% in that.
Per
Ma'am, but we
question,
get
how much
another,
marks?
Come again?
ma'am, we get another chance upcoming Sunday,
Yeah, yeah. Reattempt is there.
Then
Hello,
how much
ma'am, but
time will be
my
given?
OPP is now means this is OPP one for me.
There is only one OP in DBMS.
Then
Uh,
how much time will be given?
Time, I'm not exactly sure. I think 1 hour, right? I think it's 1 hour. I'm not exactly sure about the time. It will be mentioned. I think you can check in your mail and all. The question pattern is like that. So I would say that when you start the exam, right? So first try to complete the mandatory question, that is the Python DB question. Then you attempt the SQL ones. So easy ones are pretty easy to do. Those you can do. Now the difficult and medium ones is the challenging part. So that is where you do get the intermediate level SQL question. Intermediate, advanced we don't give, right? It's just easy and intermediate level. So week 2, week 3 questions that we practiced.
ma'am,
Yeah,
how many marks
1.5
per
hours.
question?
Yeah, sorry.
How many marks per question?
All of that is given in the grading document. Huh? Check that marks and all, check it once. I think, one second, wait, let me see if I have that document. Also, what is this? I was getting so many mails from some of you that there's some issue regarding the OP eligibility, week 7, people who didn't submit the assignment. Are all those issues resolved now? I don't have the document right now. Okay, I'll check it, but you all should have access to those documents where all this grading pattern and everything is given, right? So just check that once. And previous year OP questions, a lot of people have been asking me, but we don't actually upload those questions in the portal, right? So we take OP revision sessions. So in that session, we discuss the PYQs. If you want to practice, you can always see the previous ones.
Means like
Ma'am,
Python, how you in portal how you just send that mock test that is not available for DBMS.
Mock test for OP?
Yes, yes.
No, I don't think there is a mock test for OP.
ma'am, in week 2 and week 3's PPA questions, the images are not available.
Images are not there.
Yeah.
Okay, okay, I'll check that. Okay, that I will update. But yeah, according to the questions that I have got on Discourse, that what are the important PYQs and stuff. So all of that I will discuss in the OP sessions that are upcoming, right? I think 2 sessions will be there in next week. When is the date for your OP?
17 August.
Yeah, so then next week we'll have OP sessions only. So there we'll discuss all kinds of PYQs, but mainly you can just take up the questions that are there in the graded assignments of week 2 3, and obviously week
Check the
7.
image problem.
Yeah, that thing I will let's resolve that by today only. I'll try to do that after the session. Okay, I was not aware. Now for PythonDB we'll have a separate session again, but same things only we will discuss. The same thing that we did in week 7. Nothing different than that. Only see in PythonDB the entire format remains same, right? So you just have to remember that code that we have given. And the main thing that is going to be different in the questions is that the Python, there might be some string manipulation part, those parts might be different, but here we are not here to check your Python knowledge, right? So basically focus on the SQL query, and max to max in Python you will get those basic string manipulation. That's it. Okay, but don't miss that question. Okay, now let's start with today. I think enough people have joined. So today we are going to discuss week 9, right? So I have seen there is only one session scheduled for week 9, but it's a lot of syllabus in this 1 week. So I don't know how much I can cover. Let's try. But see, in week 9, I'll tell you what are the important topics, right? So this topic, this week is based on indexing and hashing. So first we will discuss what is indexing, what are the different types of indices, primary, secondary, multi-level, all of that. Then we have to discuss what are trees, right? So we'll start with the basic 2 3 4 tree, then we'll go up to b trees, b plus trees, how they are used to implement indices. Then we have the hashing part. So there are two parts again. So we have static hashing, dynamic hashing. Now dynamic hashing part is a bit difficult to understand, so that part I don't know if I can cover today. Let's see. And we have one more thing called bitmap index. So all these topics I have to cover in one session, so just be attentive today, okay, so that we don't have to repeat much. Let's start. So this PDF after the session, I'll give it to you. This is the same PDF that I have created from slides in the actual slides that are given to you. I have just taken the important ones. Okay, if you want it, I'll give it to you. And see, there are going to be numericals from this week. Okay, this week has very good weightage in your end term. So the numericals that are going to be there from the trees part, bt, b plus tree. So there are a lot of formula from there, right? But in the slides, certain formula are given there which are not used. I mean, those some wrong formula are there, one or two of them. So I will give you a formula sheet after this session also. You can refer to that for the exam. Okay. So now let's start. What is an index? Anyone can give a little intro. What is an index basically? Not in terms of database management, just what is index?
Position number.
Will help us to find pages in the book.
Right. So this basic book example, right? That in a book we have an index where the structure is like this. We have the chapter names and we have the page numbers, right? So a particular chapter that you want to study, you just go and find that particular chapter name and corresponding number. So this exact concept we use in database also for efficient searching, right? A table in a database might have thousands of records. If I want to access a particular record, now instead of looking through the entire database and wasting that much time and resources, we can just access the index. So to access the index, now we need some kind of a key, right? So for index we need some kind of a key. So first we have to pick out which attribute should be that key. Huh? Please mute yourself. Who is this? Okay. Yeah. So that key, first we have to pick what will be our key. Like in a book, the chapter names are the keys. Similarly, in a database management system, in a table, we'll pick an attribute from the table or a group of attributes from the table which can act as our key, that this is what we are going to use to identify. Okay. So there are different types of indices. Now we'll come to that one by one. First, see an example. Slides are visible to everyone?
Yes, ma'am.
Yes, ma'am.
See, if I have a table like this, faculty, right? So faculty table has a record number, which is the primary key of this table. We have name and we have phone number. So basically, see, in this particular table, if we take just this much data, we can say that all of these are qualified to be primary keys, right? Because all are unique information. But let's say maybe record number, name or phone number, any of them can be our primary key. Now, from this particular table, if I want to create an index on this table, so if I pick the name attribute to be my key for the index, so an index table always have records in a particular format, right? So each record in an index will have two parts. One is your key part, one is your pointer part, right? Just like in your book, key part is your chapter name, pointer part is your page number. Similarly here, key part is coming from the key that you chose, the attribute that you chose to be the unique identifier, and the pointer is the record pointer to the actual table, right? So in this faculty table, if I choose name to be my key, then this will be my index. See, all the names are there. Now corresponding pointers you see, Anupam Basu has pointer 2 because this has to point to the actual record in the main table, right? So this is the record pointer. So 2 is pointing to this. Again, Pavitra Mitra is pointing to record 6 where it is present here in the main table. Similarly, you can also create this index based on phone number as the key. That is also possible. Right, now you can either search on name or you can search on phone. So it is not necessary that it always has to be a single key. Your index key has to be single. It can also be combination. Okay. Now see, search key is what? This is the key we are talking about, the attribute to set attribute or set of attributes used to look up records in a file. Can be name, phone number, or a combination of any attributes. Now an index file consists of records called index entries. So this is an index file, this index on name is an index file. These are all records, right? Each record is of the format search key and pointer. So index files are typically much smaller than the original file because obviously we don't want to create a very big index file, right? Then it will take up a lot of memory. We want to create it small. So again, index sizes also vary on the type of index that we are creating, right? Now there are two basic, see, there will be multiple classification of indices. Now two basic classifications that we are going to deal with is ordered index and hash index. So ordered index is where the search keys are stored in a sorted order, right? Either alphabetically, increasing, decreasing, whatever you want. Some kind of a sorted order we maintain to store the search keys. That is your ordered index. Now there is something called hash index also. That is the second part, where the search keys are distributed uniformly across buckets using a hash function. Now this part you will understand when we discuss hashing, right? For now we are going to deal with what is ordered index. Now in ordered index also, index entries are stored sorted on the search key value. For example, author catalog. If I have author name as my search key, then I can arrange it alphabetically, right? Again, primary index. Now see, inside ordered indices there are again classifications based on, we'll see what it is based on, primary and secondary. There are two main types of classifications of ordered indices. Primary index, as the name suggests, that it is a sequentially ordered file. The index whose search key specifies the sequential order of the file. Now see, primary index doesn't necessarily mean that your search key is the primary key. You can use the primary key, you can use any other attribute also. Okay. Just it has to be unique identifier. That's it. Primary index is a ordered index. Ordered index means that the search keys are sorted in some order. And in primary index, the search keys are sorted in the same order as the file itself, right? If in the file, the search key is sorted in increasing alphabetical order, then in index also the search keys will be in the same increasing alphabetical order. The primary index is also known as clustering index. Okay. Now coming to secondary index. Secondary index is an index whose search key specifies an order different from the sequential order. Let's say in file, in the actual table, the search key is based on the name of the faculty. Okay. So in the actual table, the faculty name is stored in some other order. Okay, it is not stored in sorted order. Let's say it is stored according to their ID numbers in the actual file. But in the index, you are storing it in a sorted order or in some different order. That means the orders between the index and the file itself are not matching. In that case, that is called a secondary index. But when the order matches, then it is a primary index. Again, in secondary index, you can pick any key as your search key, right? Secondary index is known as non-clustering index. So this is just, remember the name, that clustering, non-clustering, that's it. And understand that why it is primary, why it is secondary. Primary is always maintaining the sequential order of the file. Secondary does not maintain it. Now, there is something also called index sequential file, which means that ordered sequential file with a primary index. This you do not require, we won't be discussing this, just the definition is enough. That it is an ordered file, sequentially ordered, having a primary index. That's called a index sequential file. But mainly when the question can come that what is difference between primary and secondary index. Then you have to say that in primary index the order is maintained, secondary it is not maintained. Now the main classification that we'll discuss, which is more important for exam point of view, is what is dense index and what is sparse index. Okay, this is another classification. So primary, secondary was a different classification. This classification is based on how the indexing is done. Now dense index means that here if I have a table which has 100 rows, in dense index also the index table itself will have 100 rows as well. That means there is one index entry for every row in the file or every row in the table. Like this example, in this table, if we have n number of rows here, if we have n number of rows, the same n number of rows will also be present in the index file. That means every index entry corresponds to every row in the actual table based on which you are making the index. Like here, what is the search key? If this is the ID attribute, this is the name attribute, this is department, this is salary. So what is the index search key we have used?
ID.
ID. Now, let's say if I ask you here, what kind of an index is this? I'm not asking dense or sparse. Is it primary or secondary?
Primary.
Because the ID order matches with the main file, right? Now see, ID is unique for every faculty. So every index entry is for a particular row only. But the trade-off here is that dense index size is very big, right? Because it has as many number of rows as the table itself. Yes, data is not same. In table there is much more data present than in the index, but it is still a pretty big index. Okay. Now the counterpart is sparse index, which is here. Now the trade-off is what? Sparse index, what happens? We have a very small index. So in sparse index, if I have a table, let's say which has 100 rows, first I will divide that table into blocks of same size. Let's say I want to create a block having 10 rows. So how many such blocks I need? 10 blocks having 10 rows each for a 100 row table, right? So now I have divided my table into 10 such blocks. Sparse index will have only one entry for a particular block. That means in sparse index, we only store the search key value for the first entry in the block. So like here, if I say, let's say this is a block. Okay, again, let's say this is a block. Now, what is the first entry in the first block? 10101. So only for that entry, we have an entry in the index table. Again, what is the first entry in the second block? 32343. For that, we have an index. Similarly, first entry in third block, 76766. So only the first entries of every block will have an index entry, right? So that means which one will take more space, sparse or dense?
Dense.
What? Dense.
Dense index will take more space. But now think something. If I want to access this record 15151, okay, then I have to first see in which block does this record fall. In the first block, what is the entry of that 10101? I can find that here. But this entry will take me to this record, not the desired record. That means inside this block, I again have to do linear search, right? I can access the first block, but inside that block, I have to do linear search until I get my desired entry. So that is an extra amount of time. What is worst case complexity of linear search? If I have n records, what is the worst case?
N square.
Worst case of linear
of n.
search. That means
N.
order
N,
of n, right? That means at most you have to go through n elements to find the match. In case the match doesn't exist, you have to go through all n elements, or in case the match is at the last element. So here that extra time complexity is taken for the linear search. Unless your desired record is the record which the pointer is pointing to, you have to perform a linear search. But now this same record, if I wanted to find in dense index 15151, I have a direct entry. So from here, I can just search in the index table and I can just directly access. So which one will take more time to search, dense or sparse?
Sparse index.
Sparse.
So that's your trade-off. In dense index, it takes more space, but the searching is more efficient. In sparse index, it takes less space, but the searching is difficult, takes more time. So when we actually implement this in real life scenario, we usually use a mix of dense and sparse indexing based on whatever our requirement is, right? So these two classifications are very important. See, the trade-off is given here also, so you can study it from here. I'm going to go a little fast because a lot of topics we have to cover. But is there a doubt? Anything we have covered till now?
Can you explain any example of secondary index?
Secondary index, see. Let me check if there is an yeah, this one. Okay, here check if this is my secondary index. Okay, so this is the ID attribute based on which I have created the index, correct? Is the okay? No, we have created salary. We have created on salary. Now, is the order of salary in the table and the order of salary in the index same?
No, it's not.
No, right? In index, we usually keep a sorted order. So this is a secondary index because we can see the order is different. Now, in secondary index, what happens? Index record will point to a bucket that contains pointer to all the actual records. Which means, see, in the actual table, you can see for 80,000. How many records are there who have 80,000 salary? One record is there, two record is there. Correct? In the index table, how many records are there for 80,000? Only one. That means now there has to be some intermediary because this 80,000 has to point to two different locations, but we don't have that many pointers. We only have one pointer here. So we have these intermediate buckets. Okay, these are the buckets. What these buckets do? For 40,000, this is pointing to one bucket. The bucket, so this pointer is the pointer to the bucket. The bucket has the actual pointer to the record. So similarly for 80,000, now why this is important? For 80,000, since I don't have space for two pointers, so I point to a bucket which has two values, two spaces, right? A bucket which has capacity 2. So here I can store the first pointer, here I can store the second pointer for the 80,000 in entries. This one and this one. Okay, so secondary
from
index,
a bucket
yeah.
to the table, there I see many arrows are there. It is a dense index, right?
Yeah, bucket to result is a dense index. Again, from this secondary to the buckets, that is also dense.
Okay. I thought initially it is a one-to-one mapping. It doesn't seem
No,
like
we
one-to-one.
cannot do one-to-one because there are multiple entries.
Correct.
Right, it has to be one-to-many.
Mm-hmm.
So
Got
first you map one-to-one to the buckets, then from buckets you map to the actual entries. This is secondary index. But the main identifier is that you can check that the attribute based on which you have created the index, the order is not same. Right.
Okay.
So secondary indices have to be dense.
Yes. Thank you.
Yeah. Now multi-level index, yeah.
Ma'am, for the record 80,000, so we have actually two records. So, I mean, in the secondary index or in the buckets, are these records sorted in some order? I mean, these values?
Could be, they can be sorted in ascending order.
Okay.
Okay. Because if you have it sorted, then obviously it is a better practice. Now, multi-level indexing is something that we won't be learning the implementation, but you should understand what it is. Multi-level index is when do we have it? When the primary index is so big that it doesn't fit in the memory. So the access becomes more expensive. My whole idea of indexing is based on that I want faster access, cheaper access, right? So I don't have to go through the entire table. If my index also becomes that huge, then there is an extra overhead cost of searching in the index only. So to avoid this cost, we have this multi-level index. That means solution is what? We will treat the primary index as a file itself. That means you are now building an index on an index, right? Primary index is indexed on the actual table. Now primary index is also being treated as a table, and there is another index built on top of that. Again, if that index is also very big, another index I'll build on top of that. So this is index to index, is multi-level indexing, right? Outer indices are usually sparse index, inner indices are dense, right? For example, let me take an example. Wait. There was some example. Okay, fine. I'll just write it. See, if this is my main table, okay. So let's say my main table has 1000 rows. Okay, 1000 rows are there. I created a dense index on this, which is my primary index. How many rows will my primary index have?
100 and 1000.
1000 rows. Dense means same number of rows. So this now becomes too big for me to store in memory. So now I want to create another level of index on top of it. But if I create a dense index, will there be any change? It will again have 1000 rows, right?
Yes.
So if I now create a sparse index, now let me divide this index into blocks of 10, each having 100 records, this one. So then in the higher level sparse index that I'm creating, how many rows will be there?
10 rows.
10 rows. 10 rows only. So this now can fit in my memory, right? And I can store this one in the disk. So in memory, I will access the smaller index, which will lead me to the disk, which is the dense index. And from dense index, I can go to the table. So that's why we have multi-level indexing when one index size becomes too big. Okay.
If we
Now-
continue to create indexes over indexes, like, won't it increase the search time?
Definitely, it does increase the search time. There is always a trade-off, right?
Right.
But that search time, now this depends on what your requirement is. Now, if you cannot avoid, you have to give that overload, right?
Okay.
So multi-level indices are not used everywhere. Usually we always try to use some kind of a mix and match of this dense and sparse. Okay. But somewhere multi-level index might be necessary if you have a table. Usually in real life scenarios, tables have millions of rows also, right? So in that case, dense index will be very large. So we have to do multi-level indexing. In fact, there are 2, 3, 4 levels of multi-level indexing. So even though the search might take time, but you see, it is a very small amount of time when you see from computational point of view. Searching in a sparse index with 10 rows will take very less time. So that is almost negligible. You won't even feel that. But memory is very efficient, right? So we cannot store all this huge data in memory because we have to use that for processes. So multi-level indexing is necessary. We'll see some numericals on multi-level indexing too, but is the theory part clear?
Yes.
Yes.
See this update delete, this is, I'll just tell you once quickly, not very important. So deleted record basically, see, when we create multi-level indices or when we create indices at all, then we have to keep in mind that if we insert some new record or delete some record, then we have to update that same in the index also, right? Now if it happens, so let's say I have a search, I have an index like this. Okay, this is a sparse index built on this table. Now let's say this person left the job, Crick left the job. So he was my pointer to the third block, right? That means now my pointer here has to shift to the next person in the third block, 83821. So this deletion has to result in an update in both the index and the table. Similarly, if I enter a new person, let's say I have 3 blocks here. Now I enter of last another person here. So now I have to create an extra block because this is the beginning of the 4th block. So for that you have to add an index entry also. So according to your insertion or deletion, the required updates have to be made in the index as well. That is only given here. So just read on that, this insertion deletion part. In dense index, search key value, if it does not appear on the index, you can directly insert it, right? Because dense is one-to-one mapping. But in sparse, there is an index entry for each block, right? So if you insert in such a block where there is already an index entry, so you're just inserting in the block itself for which there is already an entry present, so index doesn't require an update. But if a new block is being created and that is the first entry, then you have to create an entry in the sparse index, right? So that is about indices, basic indices, right? We haven't come into B3, B plus tree yet. First we have to learn what is balanced binary search tree, then 2, 3, 4 tree, then we'll come to the B3, B plus tree. So binary search trees we have discussed in week 8. All of this part you know. What is the height of balanced binary search tree with n nodes?
Log n.
Log n. That is my good tree, right? Like this. Now, in case of a skewed tree, that means where all the nodes are on one side of the tree. What is the complexity? Worst case for searching?
Order of n.
Order of.
Order of n. Right. Now these things, no need to remember this table, just go through it once, that what is the best case complexity, what are the time complexities for different operations. See, for insert delete, mostly it is constant time only, order of 1. But for searching the time varies, right? Now we have to see what is our requirement. We always want a balanced binary search tree. Balanced tree will always have height approximately order of log n. This is my desirable height. So based on that, I have two types of trees. One is the bad tree, one is the good tree. Bad tree is where the height is order of n. That is your skewed binary search tree. Means I have to go through all of the elements to reach the last element if that is what I'm searching for. In case of a good tree, the height is log n. That means every step of the search you are always discarding half of the tree. That's why it is log n, right? So good tree is what we are looking for. Now, what are the timing complexities for searching in a good tree? It is log n. For inserting, so if I want to insert a particular tree, a particular node in a tree, then I first have to find the correct position to insert, right? When we create a tree, we have to find the correct position for every node. So that searching will take log n time. On top of that, the inserting itself will take some constant time. So that is order of 1. So order of log n plus order of 1. So we don't, this constant time is negligible. So we take order of log n only. Similarly for delete, you first have to reach the node that you want to delete. For that you need searching, which will take order of log n time for a good tree. Along with that, constant time for deletion, that is order of 1. You can ignore that. So total time is order of log n. Right. See, in a binary search tree, in balanced binary search tree, all leaf nodes will have this at the same level. All leaves will be present at the same depth, right? That is the bottom level. If my last level is level 5, then all leaves in that tree should be present at level 5. Now height of all leaf nodes should be same, right? If I have n nodes, height of tree is order of log n if it is a good tree. That means that all leaf nodes are at the last level, that is order of log n. So complexity of search, insert, delete is, I already told you how it is log n, because constant time for the operations and searching time. All data is kept in sorted order. You already know binary search tree, we always insert in sorted order. Left hand side is for lower. If you have higher value, go to the right hand side of the tree. So tree is sorted. Now we will think of this tree. So till now we have seen trees like this, right? Every node has only one key value and children like this. Binary search tree, at most a node can have two children, and every node has only one search key value present in it. So now we have to think different, that now one node might have multiple keys present in it, and one node might have more than two children also, right? So that is where this BST concept will now get generalized into larger trees, larger external data structures, right? This is the beginning of your B tree and B plus tree. So B tree, B plus tree are also binary trees only, types of binary trees, right? But here we are not limited that every node will have one search key value or two children. We are not limited. So every node in a 2, 3, 4 tree. So this is the new type of tree we are going to learn, 2, 3, 4 tree. where every node, leaf or internal, is a 2 node or a 3 node or a 4 node based on the number of links or children. So instead of doing all this theoretically, let's see an example. So these are the types of nodes present in my 2343. First is a 2 node. This is a 2 node. 2 node means what? See, this name 2, it doesn't come from how many key values are there. It comes from how many children that node can have. So a 2 node can have at most 2 children. Typical binary search tree node that you have seen till now, right? So on the left hand side, if this is my search key value S, on the left hand side, I'll have values that are less than S. On right hand side, I'll have values that are greater than S. So it can have at most 2 children. Now this is a 3 node. A 3 node can have 3 children and 2 search key values. That means if I have an n node, what is the pattern? What is the maximum number of keys that node can have?
n+1.
Keys. See, in a 3 node, I can have 2 keys. In a 2 node, I can have 1 key.
n minus.
So in an n node, I'll have at most n minus 1 key. And how many maximum number of children I can have in an n node?
N children.
N children, right? So similarly, in this 3 node, you can see there are 3 different children. What are the constraints? The child on the left hand side of S will have search key that is less than S. The child on the middle, that is between S and L, it should have value that is greater than S but less than L, because it is on left hand side of L, right hand side of S. Again, the child that is on the right hand side of L should have search key greater than L. Similarly, for 4 node, you can see there are 3 values S, M, L, 3 key values. 4 children. Left hand side of S is less than S. Between S and N, M means greater than S, less than M. Between M and L means greater than M, less than L. And the last one is greater than L. So these are the 3 types of nodes. Now how will we insert? Right. So instead of doing it theoretically, let's take an example now. So this splitting part, see, in a 2343, the largest node that we can have is a 4 node, right? That is the largest node. So in a node in 2343, you can at most insert 3 key values. That is the biggest node possible. Now, what we do is there are 2 types of splitting. One is immediate splitting and one is when we don't split immediately. So what is splitting? In immediate splitting, whenever a 4 node is formed in the tree, immediately we split that node, because that is a liability. This node is a liability. Now if you have one more key value coming in which you need to insert in this node, it is not possible because this node is filled and we cannot have a higher order node. In 2343, 4 node is the highest order node. So that's why we never want to keep these 4 nodes. Every time a 4 node is formed, we split it. How do we split it? The middle key element will go 1 level up. So M will go 1 level up. Now S is definitely less than M, right? Because it is on the left hand side of M. So S can be the left child of M. And L is definitely greater than M. It is on the right hand side. So L will become the right child of M. Now, according to that, the children have to be sorted. So A and B both are less than M because both are on the left hand side of M. So I can put them as children of S, right? A is a left child of S because A is smaller than S. B is greater than S but less than M. So it is a right child of S. Similarly, C and D. C and D both are greater than M. So they are going to be right child in the right child of M. So they are children of L now. But C value is less than L, greater than M. So that is on the left child of L. D value is greater than M, greater than L, greater than both of them. So it is the right child of L. This is how node split happens. Always the middle element will go 1 level up. Okay. We do not need to split 2 nodes or 3 nodes. Only the 4 node will get splitted because that node is full. Right, a 2 node can convert into a 3 node, a 3 node can convert into a 4 node, but a 4 node cannot convert into a 5 node. That is not possible. Okay. Now, how do you split with a 2-node parent? Let's say I have a 4-node here, but the parent node is a 2-node. P is a 2-node, right? It has only one search key values, 2 children, E and this node. So now if I want to split this node, how will it happen? The middle element will go one level up. One level up where? To the parent itself. So this M value will go into the 2 node and convert it into a 3 node. Where will M enter? This node is on the left child of P. That means M is less than P, definitely. So it will be on the left hand side of this 3 node. Correspondingly, you have to also change the children here, S and L, right? Because this 3 node, when you split it, it is being split into two nodes. S and L are now 2 nodes. All this will be better understood when we see this example. Okay. This early split and late split strategy is the same thing that I said. Early split is when while you are creating the tree, every time a 4 node is formed, you immediately split it, whether you need to or not. But late split is where you keep the 4 node and you only split when some key value is trying to enter that node. Okay, but we are going to try to follow early split strategy. Both are valid and both will have same complexity. It is just they can give different results based on when you do the split. Okay, but we are going to follow early strategy. This will clear it up. See, we have to insert these values in the 2 3 4 tree. Okay, so what is the first value? 10. So 10 is my root node. After that it is 20. So what is this 10 currently? What type of a node is it? 2 node, 3 node or 4 node?
2 node.
It is a 2 node. Now I want to insert 30. 30 is greater than 10. So it will come to the right hand side of 10. Now what node is this?
3 node.
3 node. Next you want to enter 60. 60 is greater than 10, greater than 30. So it will come to the extreme right. What node is this?
4
node.
4 node. Now we are following what strategy? Early split. That means as soon as a 4 node is encountered, we have to split it. So if I split this node, which key value will go one level up? 10, 30 or 60?
The middle one, 30.
That is 30. Always the middle one. So 30 goes one level up. 30 becomes the root node. 10 comes as its left child. 60 comes as its right child. Okay. Next I have to enter 20. So 20, where can I enter? 20 is first compare with the root. Less than root. So come to left child. 20 is greater than 10. So where will 20 be entered? To the left hand side of 10 or right hand side of 10?
Right side. Right side.
Right side. So it will look like this. 10, 20. Now this has become a 3 node. Right? This is a 2 node. This is a 2 node. Next I have to enter 50. 50 is greater than root node. That means come to right child. Right child has 60. 50 is less than 60. So 50 will be included in the left hand side of 60. Now this is also a 3 node. Both are 3 nodes. But we are not going to split until we have a 4 node. Next value I have to enter is 40. So 40 is greater than 30. Right? Come to the right child. 50 and 60. 40 is less than both 50 and 60. So it comes to the left side. Okay. So 40, 50, 60. Now what node is this?
It's a 4 node.
4 node.
That means what I have to do? Split. As soon as you encounter, split it. Which value will go one level up?
50.
50. So 50 goes to the parent node. Parent node is having 30. 50 is greater than 30. 50 comes to the right hand side. 30, 50. Now this is a 3 node. Now what will happen to 40 and 60? 40 is less than 50 but greater than 30. So it becomes the middle child. 60 is greater than 30, greater than 50. So it becomes the right child. So now we have 3 node, 3 node, 2 node, 2 node. Next element is 70. So now 70 compare with the root. 70 is greater than 30, it is greater than 50. So it comes to the right hand side of 50. Here you have this node having value 60. 70 is greater than 60 as well. So it will come to the right hand side of 60 here. Look like this. So now this is also a 3 node. Next value is 80. 80 will also come to the right hand side of 70. Again we encounter a 4 node. So now when I split, what will happen? Tell me. This split is important. 70 will go up. Okay. So 70 will go up to parent node. So what will it look like? 30, 50, 70. Can I keep it like this?
No, we'll have to split it again.
Again, right? Because now this is also a 4 node. See, this is what early split strategy saves you from. Okay. So when you do early split, there are very less scenario that you have to do multiple splits in one go. But if you do late split strategy, then this will happen multiple times, that you will have to split multiple nodes to enter a single key value. Okay. Now, how will this look like? See, first 70 comes here, right? Then you split this node 70. Sorry, what did we enter last? 80. 80 comes here. We are missing one value, I think. Some 15 value was entered. Okay. After 18, they have also entered 15. So now both of these are 4 nodes. So both need to be split. So first we are splitting this node because this is the first 4 node that was formed. So 70 goes one level up to the parent. Now parent becomes a 4 node. And this is also a 4 node. This 40, 60, 80, this placement is clear for everyone, how these children are placed.
Yes.
Anyone who didn't understand how this 40, 60, 80?
Ma'am?
Yeah.
In the previous step, we had splitted that child node and 70 was pushed into the parent. After
we
that,
haven't done it yet. Okay. Here I did it because this is going to happen. Okay. It is going to happen. We haven't done yet.
Okay.
Because there are now 2 4 nodes. So we are going to do one by one. After this entering the 15, we have another 4 node. So now we are going to do the split. Now 70 is being split. So it is.
Can you explain about the 40?
Which one? Come again. Which one?
Ma'am, so this becomes late splitting, no?
Yes. This single part is late splitting, but the entire thing is following early split strategy. Look, why this is late split? Because here, as soon as we encountered the 4 node, we didn't split, right? But late split means what? This is still early split in what sense? This is a 4 node, but am I trying to enter anything else here till now? No. So I have a scope of splitting it before something else wants to enter in this node. See, what is the definition of early and late split? Early split means you split a 4 node as soon as you cross it on traversal, right? So that you ensure that the tree does not have a path with multiple 4 nodes. Late split is when you split a node when you need to insert an item in it. That is late split. So in late split, you will split only when you need to insert one more item in the node and the node is full. But see, in this example, here, this node has 60, 70, 80, but the next item is 15, right? Is 15 trying to enter in this node? No. 15 is trying to enter in another node. So we are not immediately splitting, but this is also not late split. Late split is when you want to enter something and then you feel that, okay, there is no space, so I have to split. Right? It is not technically late split. Now, if after 80, 90 came, then it would have become late split if I didn't split it by then. After 80, there is 15. So first the 2 4 nodes are created. Then I start the splitting. So then 70 will go one level up. So 70 comes in the root node. Now root node becomes 4 node and this is also 4 node. So at this point, you are entering 90 here. 90 can come, but these two also have to be splitted, right? So here again you are doing early split strategy. See, there are no more insertion required. In root node we are not inserting anything, right? The 100 can easily come here. Now root node is splitted. So which will go one level up? 50 will go one level up. What is the left child? 30. right child 70. Now 30 will have left child this 10, 15, 20, right child 40. And 70 will have left child 60, right child 80, 90. Now you want to enter 100. So we still haven't split this node, right? This node is still there, 4 node. Now split for 100 when we do. 100 can come here, resulting in another 4 node. But am I going to split anymore? No, because now my tree is complete. There are no more insertions I'm going to do. So that's why we didn't split these nodes as soon as we saw them, because these are not initial nodes. I can see that these are the nodes I want to enter, these are the key values I want to enter, and I am at the end of it. And 2, 3, 4 tree can have 2, 3, 4, 3 types of nodes. So I only follow the early split strategy when I have many more values coming, right, to enter in future. But after these 4 nodes are formed, there are no more values to enter. So the tree is full. I'm not entering anything else. So I can stop here. I don't need to split again. This is a valid tree. Now why we did this 2, 3, 4 tree? This will not come in exam. This is not a valid thing basically. It is not there in any exams. You cannot find this in the syllabus, right? There is nothing called 2, 3, 4 tree. We just created this to give you an idea of what is B tree and B plus tree, because now you are familiar with nodes that have multiple key values, right? A 2 node can have 1 key value, a 3 node can have 2 key values, a 4 node can have 3 key values. So similarly, now you can generalize this idea that an n node can have n minus 1 key values. Up to this, is it clear for everyone?
Ma'am, can you please move for above slide, ma'am?
Sorry, come again.
Back slide, ma'am. Previous slide.
This one, yeah.
Yes, ma'am.
Yeah,
After
tell me which
80,
part?
ma'am. After
After
80.
80. Okay.
15,
See,
15
here I had 80 is inserted, right, in this tree. Now I also inserted 15 here. See, let's come to this one. This is the last one. Up to this you understood?
Yes, ma'am.
Okay. So now we have this 4 node where I entered the 80. Next value I need to enter is 15. So I have not done the split yet. So this is the tree with 1 4 node. I have not done the split yet. Next is 15. So compare with the root. 15 is less than 30. So go to the left child of 30. That is this node. Here 15 is greater than 10, less than 20. So it will become the middle element. So now it looks like this: 10, 15, 20, 60, 70, 80. So there are now 2 4 nodes. Now I will split this 4 node, because the next item I need to enter is 90. So I am splitting this beforehand. Now when I split this, 70 will be the middle element, which has to go 1 level up to the parent. So 70 comes here. 70 is greater than 30 and 50, so it becomes the right hand side element. 40 will become the child that falls between 30 and 50. 60 here, this node, this 4 node has now broken into 2 nodes, right? 60 is 1 2 node, which becomes a child that is between 50 and 70. 80 is a 2 node, which is the child that is on the right hand side of 70. Same BST, left child is smaller, right child is bigger. Now also you have 2 4 nodes. One is the root one is the leaf one, right? Next value
Yes,
I'm trying to enter is 90. So 90, if you compare with the root, 90 if I compare with the root, it will tell me to enter it here, right? It is greater than 70, so it has to come to the right child. But what am I doing? First, you enter this 90 to this child, then you split the root node itself. So the root node is splitted. Now the middle value goes 1 level up. So 50 becomes the root node. Its left child is 30. Its right child is 70. 30 has 2 children again. Which one? 10, 15, 20. This 4 node, which is the left child of 30, all values less than 30. And 40, which is greater than 30 but less than 50. So this is the right child of 30. Similarly, for 70, which is the right child of 50, what are the children? Left child is 60, which is less than 70. Right child is 80 and 90, which is greater than 70. Last you have to enter is 100. So again compare with the root. 100 is greater than 50, come to right child. 100 is greater than 70, come to right child. Here 100 is greater than 80 and 90, so it becomes the last element in this node. So this is the resulting tree. Now these 4 nodes, I have no requirement to split these. Okay, because now the
Okay.
tree is complete.
Yes.
So from this, is it clear everyone? Anyone has a doubt till now? Okay. This deletion I will tell you. Okay, let's quickly do this once. Look, see, if I want to delete some node, okay, then we have to locate the node n that contains the item that I want to delete. So in order successor, we have to find the particular item's in order successor. That means in order traversal we have to know. So are you familiar with what is in order traversal? Anyone here?
Yes,
Tree
ma'am.
traversal.
Yes.
So there are 3 types of tree traversal, right? Post order, pre order, and in order. Okay. So when I traverse a tree in order traversal, then the node which will come after the item that I want to delete, that will be its in order successor. I am not telling you what are those different traversal algorithms because that is not required in DBMS. You will learn that in PDSA, right? We'll have that there. So that in order successor is the item that I will swap this with. That means if you are deleting a node, it will be swapped with its in order successor. 1 second, I'll give you a small example. Okay. See, if this is a tree, I'm just taking a small tree, 1, 2, 3. Okay. If I do in order traversal of this, then the output will be 2, 1, 3. Goes in this way. Okay. In order means you first start with the left child, then the middle root, then the right child. This is in order traversal. So in case of in order traversal, if I want to, let's say, delete the value 1. Okay, if I want to delete the node 1, so it has to be swapped with its in order successor. Who is its in order successor? 3. Next node. So now 3 becomes the root and 2 will remain as it is. It is still maintaining the order. 2 is less than 3. Right. Although this is not a correct example because 1 is less than 2, so it cannot be the child. But this is how the in order successor will always swap the deleted item. Okay, and it will maintain the order. Don't take this example correctly because this is the values are not correct. This is not a correct BST. But in order traversal happens like this: first the left child, then the middle one, then right child. Okay. Now this part is not required. Yeah, these formula. This is what I'm talking about. So these formula that are given, don't go through these. Go through the sheet that I will give you. Okay, because some formula are wrong here. This seal value, floor value, some values are wrong here. I'll give that. What we have to basically learn is, see, these questions will not come from your 2, 3, 4 tree. Questions will come from B tree, B plus tree. Right. So for B tree and B plus tree, I'll give you separate formula. First, let's understand what is B tree, what is B plus tree. So we'll start with B plus tree. So B plus tree is a balanced binary search tree. Okay. It follows multi-level index format. So this is why we understood multi-level indexing beforehand, right? All the indices that we understood, primary, secondary, dense, sparse, multi-level, whatever, all of those can be implemented using these trees, right? So when I say B tree follows a multi-level index like 2, 3, 4 tree, that means, see, this is the outer level index, this is the inner level index. So here outer level index is pointing to the first key of inner level index every block. See, this one is pointing to the first key, this one is pointing to the first one. So this is the sparse one, this is the dense one. Think of it like that. Every tree, B plus tree, is a multi-level index. How it works, we'll see with some examples. in B plus tree, the leaf node. So now what is the data? Where are the data stored? These key values are your data. These are the search keys in the index, right? A, B, C, D, E. These are all search keys of the index. This is how index is implemented. So D and G, you can see they are present in the root, but they're also present in the leaf. Why? Because in B tree, in B plus tree, only the leaf nodes have pointed to actual records. That means this root node is pointing to its child node. These are child pointers, block pointers. But the leaf nodes are the record pointers. So when I come to leaf node, this will show me that this D record is where is it actually stored in the table. Here that record pointer will be present. This one is pointing to the actual table in the disk. Okay, so in B plus tree, what happens? Every node has copies, right? Every key value has copies. But we must maintain that the leaf node or the nodes, all the leaf nodes at the leaf level, should have a copy of each internal node, because only leaf nodes have pointed to the actual values that are stored in the table. You'll understand how it actually works. Let me take a better tree. Mm, yeah, for example, this one, let's take. See, in this tree, 25, 50, 75, these are at the root level. But we can also find copies of these at the leaf level. Here, 25 is also present, 50 is also present, 75 is also present. See, this pointer is pointing to this node. This pointer is pointing to this node. These are all node or block pointers, right? But the pointers that are associated with the leaf nodes, these are the leaf nodes. They are pointing to the actual records in the table. But in B plus tree, there is one specialty of B plus tree is you can see all the leaf nodes are connected. See this arrow? This leaf node is pointing to the next leaf node. This leaf node is pointing to the next leaf node. So can you tell me a data structure where we can implement like this, where the one node
Linked
points to the
list.
next node? Linked list. That means leaf nodes use linked list in case of B plus tree. All the leaf nodes are linked using a linked list. Why this is done? So that we can have random access as well as sequential access. So in linked list, is random access possible?
No, ma'am, because we need pointers to reach to different
Reach
nodes.
to the next node, right? So we always have to go sequentially,
Yes.
right? But this linked list structure is only there in the leaf nodes. In the other nodes, you can randomly access any key value. So
Yes.
this
Yes.
gives you both sequential and random access. Okay, this is specialty of B plus tree. In B tree, this linked list format is not there. So in B plus tree, there are some characteristics that you should remember. First thing is, in B plus tree, leaf nodes are joined using linked list. Second one is all internal node key values will have duplicates in the leaves. Third point is what? Only leaf nodes have record pointers. This is very important. This question has come multiple times, that which node has record pointer in a B plus tree? Only the leaf nodes. Record pointer means pointers that are pointing to the actual record in the table that is stored in the disk. Internal nodes have child or block pointers. These are some important points regarding your B plus tree, right? Leaf nodes are always going to be at the same height. So again, these things, see, internal node can contain at least n by 2 child pointers. So at least every internal node should be half filled, right? N is called the order of the tree. See, in every question you will see that B tree of order n, B plus tree of order n. What does this mean? What is this n? So if I say that this particular tree is of order 4. What does that mean? Every node can have at most 4 children. See, there are 4 pointers. 1, 2, 3, 4. This one. Every node can have at most 4 children, and at most how many key values?
3.
3. N minus 1. So if order of a tree is n, it can have at most n children or child pointers, and it can have at most n minus 1 keys. This formula is same for B tree as well as B plus tree. Okay. Now there are some regulations that every internal node means every node other than the leaf nodes. Every other node is internal node. So every internal node must be half filled. That means at least n by 2 child pointers should be present, except for the root node. Root node can have even one child pointer. Okay, that is the minimum for root node. But at most an internal node can contain n child pointers, because n children, so n child pointers at most. Again, these are all approximate values. Leaf node, at least a leaf node should contain n by 2 record pointers, that is half filled again, and n by 2 key values. So every leaf node should be half filled. And at most, leaf node can also have n record pointers and n key values. Right? Not n, this should be n minus 1. Leaf node order is same. No? So at most you can have n minus 1 key values. That's why I'm saying that don't study these things from here. I will give a formula sheet. Some mistakes are there. Okay. So these arrows that you're seeing, these are called block or child pointers. And these are the pointers which are actually pointing to the records in the table. And this last pointer is for the leaf node connection. So every leaf node will have this extra pointer which points to the next leaf. Now suppose we have to search 55 in the B plus tree given here. Okay. How will you do that? Start with the root node, right? So in root node 25, 50, 75. So you tell me between which two key values can I find 55? Where should 55 lie?
50 and
Between
75.
50 and 75.
50 and 75.
50 and 75, right? Just a second. Yeah. Okay. So 55 can be found between 50 and 75 because it is greater than 50, less than 75. So this pointer, this child pointer will lead me to 55, the node containing 55. And then again in this node, how will I search? Linearly, I have to search. First search 50, then search 55. Right? So you have to first reach the desired node. Then inside the node, you have to linearly search. Now, B tree insertion, how does it happen? If this is my tree, I want to insert the value 60. Now remember the split that we did, right? See, just looking at this B plus tree, can you tell me what is the order of this tree?
4. Because at leaf has 4 keys.
So that is that what I said? This was the formula.
Oh,
If
sorry.
I can have at most n minus 1 keys, order is n, right? So what is the order?
5.
5. Okay. Now I want to insert 60. So whenever we do insertion, that has to happen at the leaf level, right? So we'll start searching from this. Start searching from here. Root node. So 60, where should it come? It is greater than 25, it is greater than 50, but it is less than 75. That means this child pointer. So 60 should be inserted in this node. This is the leaf node. Insertion always happens at leaf. Now in this node, what is the particular node? 55 but less than 65. That means this middle node part between 50 and 65. I need to enter 60, but this node is filled. So now what do I do? And I need to insert something. Then what do we do?
Split.
Split the node. Now here the interesting part is when we want to split, first we have to create the intermediate stage. That what if I could insert 60? Then what would be the structure of this node? This is the intermediate structure. If I had 5 key values in this particular node, so I'll have 50, 55, 60, 65, 70. This is not possible, but this is the intermediate structure which would have formed if I could enter 60, right? Now, what is the middle element here
60.
in the intermediate node? 60 is the middle element. So 60 will go one level up. So this is how we calculate the middle element here, right? You have to create the intermediate node. That what could have happened. So suppose we want to enter a record 60. So it goes to this leaf node, right? Leaf node of this tree is already full, so we cannot insert 60. So we have to split the leaf node. So if we entered 60, then if we entered 60, then the so middle element, this will go to the root. Okay, let me write it here only. So if I take 60 to the root, first tell me where will 60 enter in the root in this.
Between 50 and 75.
So now root should become like this: 25, 50, 60, 75, right? This child will remain same, this child will remain same. What will happen to this child, this leaf node? How will it be split? 50 and 55 will get split to a separate node. 65 and 70 will be a different node. So 50 and 55 can come as children of here between 50 and 60.
Yes.
Here I can have 50 and 55 sleeve. See, this is the structure. 50 and 55 here, 65 and 70 here. But why is there another 60 here?
Because every key has to be present in leaf node.
Because every key has to be present in leaf. So we have to have a copy of 60 in the leaf, because only leaf nodes have record pointers. Right. Now, based on this concept, there is something called biasing, left biasing, right biasing. How does that work? This particular tree is right biased. Why? Because when we split a node and it goes above one level, and we need to maintain a copy of that node in one of the children, then which child we pick? We can pick the left child or we can pick the right child, because the copy is easy to enter. It can go as the left child element, or it can go as the right child element. Here, which child have I picked to enter 60? Right child.
Right child.
So this
Successor.
tree is right biased. Yes, so this tree is right biased. Similarly for 50, see, copy of 50 is present on the right child of 50. This tree is definitely right biased. 25 present as right child of 25. 75 present as right child of 75. Similarly, I could have stored them in the left child also, but whatever you choose, you have to maintain that throughout the tree. Either it is left biased or it is right biased. In exam, we will mention which biasing we are following. Okay. Now, 60 is entered. Okay, so the tree looks like this. 50 and 55 come as left child of 60, and 65 and 70 and 60's own copy come as the right child of 60. Now here, let me say if I want to enter, let's say 92. So first we'll check in the root. Okay, where will it lead me? Which node should 92 come in?
After 70.
This node. In this node, is it possible to enter?
No, ma'am. We'll have to make a split.
So which will be the middle element when I make the split?
90.
First create the correct. So first create the intermediate node. 75, 80, 90, then 92, then 95. Out of this, the middle element is 90. So 90 will go one level up. Can I enter 90 here also? No. But intermediate if I create, what becomes the middle element? 60.
60.
So 60 will go one level up. Then the height of the tree will change. This is how insertion works in B plus tree. Is it clear for everyone? Insertion.
Can you please explain how this
Any
middle
doubt?
element become 60?
Which one? In this 92 if I want to enter? This one.
Mhm.
So first if I want to enter 92, it has to come in this node, right? But this node is already filled. So I am creating an intermediate node that if I could enter 92 in this node, then how will it look? It will look like this: 75, 80, 90, 92, then 95, right? Out of this, which is the middle
Okay,
element? 90.
90.
So 90 will go one level up to the root, but root is also filled. So again, you create the intermediate stage: 25, 50, 60, 75, 90. Out of this, what is
So
the middle element? 60. So
60.
60 will now become the root. Okay, that means the height of the tree is now changing. So next tree, 60 will be the root. Left child of 60 will be 25, 50. Right child of 60 will be 60, 75. Like this. So that means there will be multiple copies of 60 now. This is insertion. Now
Okay.
deletion will also be kind of similar. Any other doubt in this insertion part? See, today I don't have much time, so I am just trying to finish all this. But in the revision session, I will take a series of numbers and we'll learn how to create a B plus tree. Okay, we'll do the insertion by ourselves. That is the best way to learn. Or you can check out the previous session if you want to know now. Then just go check out the previous sessions of the other terms where we had time, so we did that.
Okay.
Anyways, I'll do it in revision session once. Okay. So deletion is like what? Here from this tree, if I want to delete the node 60. So from how many places do I have to delete?
2 places. From that node and from the leaf.
Here also, here also. Correct. So first to delete 60, we have to remove 60 from intermediate as well as fourth leaf node. That is this one. If we remove it from intermediate node, then the tree will not remain a B plus tree. That means here if I remove, right, and I don't rearrange, then this doesn't remain a valid tree. So I have to rearrange the tree. So now this place is empty after I take it out, after I take 60 out. So now 75 will shift one side to the left, right? 25, 50, 75. These two nodes, nothing is changing. These two leaves are same. But this leaf will now merge with this leaf. So 55, 50, 55, 65, 70 will all now become left child of 75. And 75, 80, 90, 95, this becomes the right child of 75. This was already the right child of 75. So only the two nodes which were children of 60, once you delete 60, those two nodes will merge. Okay.
Ma'am,
And become the left child. Yeah.
ma'am, in leaf we could have had n by 2 elements. So why do we need to merge it? Because if we already have 65 and 70, we could have taken the 65
So
above.
where will you keep it?
65 in place of 60, ma'am.
Why will I do a split?
Ma'am,
No,
no,
no.
ma'am.
I am
When
asking.
we were
When I
deleting
delete
60,
the 60,
yes, ma'am. We wanted to have a that in order successor in the child. So what we do is we copy that in order successor, which is 65 in this case. We could have copied in the internal node. So 65 would have replaced 60. Now we still maintain that n by 2 must be in leaf. So n by 2 elements are still there in leaf, and the tree is valid.
but we have to always rearrange the nodes like it was before 60 came in. See, 65 was never in the root node itself, right?
Yes, yes,
75
correct.
is there. 60 came because of the split we had to do when we entered the structure. Before we entered 60, this 25, 50, 75. So once you delete 60, we have to rearrange the tree back to the same structure.
Okay, ma'am, got
Okay.
it, ma'am.
When that in order successor will happen is when you delete a node from here. Let's say in the leaf I'm deleting some node which is not there in the above levels. But here 60, when it goes away, this place will become a blank if we don't move 75 one place to the left, and that is not a valid tree design. We cannot have 25, 50 blank 75. All the nodes have to be in one side. Tree has to be filled like this from the left to the right. Right. So n by 2, that means at least every node should be half filled. Now once I move 75 to the left side, now this part, these two children, right, they don't have separate pointers anymore. Only 75 has one pointer. So both of these have to fit in this. 75 is gone, 60 is gone. See, how do we implement b plus tree as an actual index if this is the table, right? And we want to form index based on this table, and we want to implement that index in the form of b plus tree. So what do we do? Look at this index. This is the root. These are the internal nodes. These are the leaf nodes. All are at the same level, leaf nodes. Right. So Mozart, how many copies can you see? One copy, two copy. Right. Gold, how many copies? One copy, two copy. All the intermediate key values have a single copy in the leaf. And also there are definitely unique elements in the leaf also, like brand, Calipari, they don't have intermediate copies. They are present only in the leaf. But you see, only the leaf nodes have the pointers to the actual table. So this is just the replier pointing to the child pointers, that is child nodes, not actual blocks, right? So these are the block pointers, these are the record pointers. Don't go through all of this. I will give this formula sheet. This part also. See, this one formula is very important. So this is a correct formula. So if there are k search key values in the file and the height, tree height is no more than this, so b tree contains relatively small number of levels, right? This is the whole point. Why we use trees which have multiple key values stored in a same node, so that the height doesn't grow exponentially. If one node can store multiple keys, then the height won't increase so fast, right? Because one node can keep on inserting multiple keys in it without increasing the height. So if there are k search key values, then the tree height will never exceed this log of n by 2 seal of k, right? Log of k base n by 2 sealing, and the entire thing also will take the seal value. So based on this one, multiple numericals have come in pyq. You can try to solve those. Very easy numerical. They will tell you that okay, my key has, let's say, some 10,000 search key values, and there are this many nodes present. So now you find out what is the height of the tree. So you know n value, you know k value, just put it here and find out. Other than that, this formula I'll give you. Now coming to B trees, some things are different. So it is also balanced binary search tree. But in B tree, there will be no duplicates. So intermediate node will have no copy in the leaf node. So what can you understand from here? If every key value is unique, that means every node should have record pointer also. Isn't that true? That
Yes,
means
ma'am.
from every node, every key value is unique, right? There is no copy of that. That means that only appears once. So along with that key value, we must have the record pointer to the actual table. So every node in a B tree will have a different structure like this. This is a generalized B tree node. Okay. You will have one key value. Okay. This is the block pointer, which is pointing to the left child. This is the P1 is what? Record pointer. Right, pointer, the record pointer. Okay. What are they saying? Pointer BI at the bucket or file record. Okay, just the opposite. K is the key value, K1, K2, like this, K m minus 1. If there are m minus 1 number of keys, then what is the order of the tree? Each node can have at max m minus 1 keys. That means what is the order of
M,
tree?
M.
M. So see, how many p's are there? M. That means p can only be our child pointer, because a tree of order m can have at most m number of children. So pi is the child or block pointer. How many b pointers are there? B1, B2 up to bm minus 1. That means these are what? Bucket or record pointers. So this K1 key, where is this key present in the table? That is being shown by this record pointer B1. K2 key, where is it stored in the actual table? That is shown by the record pointer B2. So like this, B minus 1 number of record pointers will be there if there are M minus 1 keys. So similarly, every key should be associated with two children, right? P1 and P2. You will have block pointers. This is the internal structure of the node. Looks like this. See, now there are 2 pointers each. So for Einstein, this is the record pointer. Then this is the child pointer. This is pointing to the next node in the next level. Again, on the right hand side of Einstein, this is the right child pointer. For cats, this is the record pointer on the left hand side. Right hand side, this is the right child pointer. Similarly for Sing, that means leaf nodes, they don't have children, right? So they only have one pointer each. So this is
Ma'am,
Brand, Calipari, all of these. Yeah.
ma'am, your voice is breaking, ma'am.
Am I audible now?
Yeah, ma'am, audible.
Is my voice breaking for everyone?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Wait, let me
Yes, ma'am.
rejoin. One second.
Is this better? Can you hear?
Yes, ma'am.
Yes, ma'am.
Actually, my internet is off, so I am having to use the phone data. Might be because of that. Okay, you let me know, okay, at any point if I am not audible. Alright. See, this is the B tree and B plus tree structure based on the same data, right? There is one mistake here though, that in this particular diagram, B tree doesn't have these linked lists that is present in B plus tree. It should not be here. Linked list structure is only there in B plus tree. See, in B tree and B plus tree, the same index is formed using the same data. So what are the differences that you can see? What is the first difference? same data is used to form indices, one using B tree, one using B plus tree. So what is the difference you can see?
The root part is not repeated in the leaf. Like Mozart is
That means
there,
any of
but
the
internal nodes don't have
intermediate
it.
node values are not repeated. Yes. So internal nodes, whatever keys are present in internal nodes, they are not repeated, right? That means B tree has, but B plus tree there is repetition. What is the other difference you can see?
There are
Any
record
other difference
pointers in
between these two trees?
intermediate nodes.
Record pointers in intermediate nodes. Here, record pointers only in leaf nodes. That is one thing. Another thing is, which is given wrong here, link list. So this is the comparison. Now B tree, B plus tree. Again, I'm telling you, today I don't have the time, so I'm not going into detail. But
Ma'am, your voice is breaking,
if
ma'am.
you want to see
Again.
the creation, just check out the last time videos or in this term. Right. I'll just join from another device. Try. Is it better now? Can you hear? I don't know why
We can hear, but there's some background noise.
Okay, one second. Now, is it clear?
Yes, ma'am. Clear, ma'am.
Yes.
Okay. See, yeah. So I was saying that please go to the last session, last term or term before that. Any of the week 9 sessions, you can find the creation of B tree B plus tree video. Okay, and in this term we will do in the revision session. Then we'll have time. But for now, this information is also enough. After the session, I'll give you the for. In hashing, what happens? It is a different type of index. Okay, hash index. So now in hashing, there is a video we have uploaded on static hashing in our YouTube channel also. You can see that. In that video, static hashing is very static, right? So static hashing, what happens? There are multiple the search key values that we have, right? The search key values are will generate certain values. These values will be used to assign buckets to the search keys. So this hash function is the main important thing here. So whatever hash function we choose, we have to be very careful about generate UC. Okay, let's start from here only. So this here, these are the keys, the names, right? John Smith, John Smith, Lisa Smith. These are all keys. Now these keys are all passed through some hash function here, which is not given, and they generate some hash values, right? So given key k and hk is called the hash value. H is the hash function, h of k will give you the hash value. If for two keys, k1 and k2, let's say for these two keys, John Smith and Sam Doe, for these two keys, if I pass them through this hash function h, for key k1 and k2, if hash function generates same values, h of k1 is same as h of k2, then it will result in a collision. So that's why we have to be careful about the hash function that we choose, right? The hash function that we choose should always want such a hash function which gives unique hash values for every search key, but that is not possible. I mean, that type of ideal hash function can only be randomly found. You cannot generate those. Okay, so we try to find a slightly better, like we try to do as good as we can, that we can get as near to a uniform distribution as we can. Let's say if I have 8 buckets, okay, if I have 8 buckets, each bucket has capacity of holding 2 search key values. Now my hash function, I would want it ideally such that if I have 16 key values, I would want that I pass each of these key values through my hash function and it will generate a value and it will be assigned to a unique bucket. So we would want that every bucket will be first half filled. That is, all the buckets have capacity of holding 2 records, like I'm saying, right? So now first 8 values that I pick, 8 search key values, I put them through the hash function. These values will be assigned to 8 different buckets. We don't want all of them to be assigned to the same bucket. A bad hash function will generate the same value for every search key. So all of these collisions will occur. That means collision occurs when 2 search key values are assigned to the same bucket, or more than 2 search key values are assigned to the same bucket. So our goal is to keep our hash function collision free but fast, right? So how does this happen? See here, can you, in this example, can you see a collision happening between which 2 search key values?
John Smith and
John Smith and
D.
Yes. So according to this example, there is some hash function which takes these 2 keys. Let's call it k1 and k2. These 2 keys, when you pass through hash function h, they both point to this bucket, bucket number 2. That means these both have created the same hash value. So h of k1, whatever that value is same as h of k2. So both of them are pointing to same bucket number 2. So this is what we want to avoid. Collision is what we don't want. Bucket is nothing but a unit of storage. Okay, a bucket can have any capacity. We'll mention that in the question, that a bucket has capacity of holding 2 records, 3 records, can have any capacity. Now it is typically nothing but a disk block only. Okay, like a bucket in where we are storing all these indices, hash indices, all are stored in a disk, right? So these are all disk blocks, but we call them units of storage, where we can give you the capacity that every bucket will have a certain capacity of holding a number of records. But whatever is the capacity of one bucket, that should be uniform throughout all the buckets, right? So if in my hash index, a bucket can hold 2 records, that means every bucket can hold 2 records only. No more, no less. Now hash function, in a hash file organization, we obtain the bucket. So how do I know that which search key I should assign to which bucket? That will be told to us by the hash function. So we first run the search key through the hash function. That will generate some hash value which is associated to a bucket. That means each bucket has some hash value associated with it. Whichever search key coincides with that hash value will be assigned to that particular bucket. So hash function h is a function from the set of all search key values to the set of all bucket addresses. See, this is what is happening, right? K1, K2 up to Kn. This is the set of all search keys. Then let's say there are bucket addresses B1, B2, B3 up to Bn. These are set of bucket addresses. H is the hash function. So every key will come to H, run function H with K with the corresponding key K1. Whatever hash value is generated will map it to one of the buckets. So H is a function from set of all search key values to the set of all bucket addresses. Okay. Now records with different search key values, if they are mapped to the same bucket, right? A bucket might have a capacity of holding, let's say, 10 records. A bucket can hold 10 records. So in that case, different search key values are mapped to that same bucket, right? Multiple entries. So now if you want to search for a particular search key, you have to go through linearly through the bucket sequentially to locate that record. So that is a different overhead. That's why we like to keep the bucket size small. Okay, this is all about static hashing. Now let's take some example. Why is it called static hashing? First of all, because the bucket size is fixed, right? The bucket size is always fixed. Your bucket can hold only a certain number of records, and also the number of buckets is fixed. So if you start with 10 buckets, after you have completed or while you are doing the hash table organization, you have those 10 buckets only, right? You cannot increase or decrease the number of buckets. So what does this do? What do you think is the disadvantage of this? So we have to initially give the number of buckets. So what is the disadvantage?
Number of records, we'll have to maintain a certain number of records. I mean, after beyond which we cannot add.
That means, right. So that means if I start my table with 100 rows, let's say, over time that can increase, right? I will insert new data, but the hash table will only have 10 buckets. So I will not be able to assign the extra data. When I want to do the hash table organization for the new records that I've entered, I won't have space left. Or what can happen is if I firstly issue a large number of buckets so that I don't run out of space, but then I'm not using them, then all that extra memory is being wasted in the disk because those are already allocated, right? So this is why, since the number of buckets is static, it is called static hashing. And for these disadvantages, this is the trade-off that we have to face. So that's why we go on to something called dynamic or extendable hashing to fix these problems, this static number of buckets, right? But for now, let's stick with static hashing. So let's say there is a file called instructor file or instructor table where we use department name as the key. Okay, and there are 10 buckets. Now binary representation of the ith character is being assumed to be integer I. Basically, this is the hash function that they're saying. Okay. Hash function returns the sum of the binary representation of characters modulo 10. Okay. That means you take the binary representation of each of these and take the mod 10 of that. That is your hash function. So sum of binary representation modulo 10. Whatever you get, that is your hash value. According to that, you have to assign to the buckets. For like music, if we find the binary representation of all the characters and find the sum of it, and then we do modulo 10, then it will give me the value 1, which is associated to some bucket. That is the address for some bucket. For history also, for physics also, if you find out, for physics and electrical engineering, apparently, if you find the sum of binary representations and then do mod 10, both are giving 3. That means both of these will be assigned to bucket number 3. There is a better example here. See. I think it was... yeah, this one. In this one, this is the actual table. How many buckets do we have? How many unique buckets are there? 8. Why there are 8 buckets? See, what is the hash function? Hash index is being created on instructor table on attribute ID. That means this is the search key attribute, right? Computed, what is the hash function? You compute by adding the digits modulo 8. That means take the first ID, 76766. What is the sum of digits? 18 plus 14, that is 32. 32 modulo 8 is what?
0.
0. So that is bucket number 0. See, bucket 0 has this search key. So since my sample space is modulo 8, so modulo 8 can take up to how many values?
0 to 7.
0 to 7. So total of 8 buckets. So that's why we have 8 unique buckets, because modulo 8 will give only these 8 unique values, 0 up to 7, right? So we can have at most that many buckets, at most that many unique buckets. Similarly, see for this one, Now check for 15151. This record, Mozart. What is the hash key? Hash value? 1 plus 5
30.
plus 1 plus 5 plus 1.
13.
13 mod 8 is
5.
what? 5. So this is assigned to bucket number 5. Similarly, 3, 3, 4, 5, 6. This one is also assigned to bucket number 5. If you find the sum mod 8, that will give bucket 5. Next, we have another one which is called this one, 58583. Right? This, Caliphate, 58583. So if I find the sum of this, what is this?
29.
29. Mod 8 is 5.
Yes.
So this is also saying bucket 5, but bucket 5 is filled. Here every bucket has a capacity of 2 records only. So at this point, this is an overflow, right? When a bucket is filled, but more records are pointing to that bucket, then this is called a bucket overflow. We handle this by something called an overflow chaining. So now you create another bucket and link it with a linked list to this bucket 5. So basically this is another bucket 5 only. This is an extension of this bucket 5. So when you have an overflow, you create a bucket of the same size and you link it with that bucket which has overflowed. So this is called overflow chaining, this thing. Now again,
Sum by modulo of number of buckets formula.
Formula is here the hash function is computed by adding the digits modulo 8, adding the digits of attribute ID modulo 8.
Means that they will give, ma'am, or seeing the buckets we need to count and we need to say either 8 or
No, they will give you the hash function. No, we'll give you the hash function. Okay, hash function and search key will give you. Okay. So like this, we can do multiple chainings. After this, if this bucket is also filled, we can create another bucket and again do another linked list chaining like this. But this increases the cost overhead when you're trying to access, right? Because you have to do a linear search, then again go into this bucket using the linked list, again do a linear search. But this is one way of handling. Now, come here. See, these parts, these two slides, whatever is said here, right? Hash function, ideal hash function should be uniform. That is, each bucket is assigned the same number of search key values from the set of all possible values, right? That is what I was saying, that if I have 8 buckets, I wouldn't want that my hash function will map all the search keys to one bucket. I want all of them to be uniformly distributed among these 8 buckets. An ideal hash function should do that. But ideal hash function is random, right? Cannot generate these functions. These are randomly found. So each bucket will have the same number of records assigned to it, irrespective of the actual distribution. So all of this part, I'm just asking you, please check out that one video we have on static hashing on the channel. Right there, I have explained all of this in more detail. I think you'll be understanding better. There is a time crunch here, but I hope at least the idea of it is clear, that what type of a hash function we want, right? We want to reduce collision basically, and we want to reduce this overflow. Here, whenever collision happens, that means 2 search keys are mapped to the same bucket. If this happens multiple times, that is when we get overflow, right? That is, one bucket is filled and still more records are trying to access it. So we have to do this overflow chaining. So this is what we want to get rid of. So bucket overflow can occur in some instances. Like one instance is there are insufficient number of buckets. If you have 10 buckets and you have 1,000,000 records, there is bound to be overflow no matter what your hash function is. It will be an overflow because bucket size is too small. Again, or number of buckets is too small. Again, if there is a skew in distribution of records. So skew in distribution of record means if there are n number of search key values k1 to kn and all of them are being assigned to the same bucket, that means there is some skewed distribution happening here. What do I mean by skewed distribution? This can happen due to 2 different reasons. One thing is multiple records have the same search key value, right? So it is not necessary for us to assign primary key as the search key. So we might choose an attribute where there are duplicate values, right? So all of those duplicate search keys will give the same hash value when you pass them through the function, right? If I have 5 If I have two search keys that are both 5, if I do 5 mod 8, in both cases I'll get 5 only, right? So both of these will point to the same bucket. So if I have multiple records having same search key value, that can cause a skew in the distribution. Or if the hash function produces non-uniform distribution, if the hash function itself is bad, it is such a skewed function that it distributes all of the search key values to only one bucket or two buckets. So all of these things we want to avoid. Now overflow chaining I explained with that example. So overflow, whenever the overflow happens, the buckets are chained together in a linked list. So this is called closed hashing, but there was some mistake here in this slide. I will update it. Now this is the structure, right? So if bucket 1 overflows, you will create an exactly same bucket and link it with linked list. Like this, you can go on with as many buckets as you need to complete the distribution. So deficiencies of static hashing, I already told you what are the deficiencies, that the bucket size, number of buckets is always fixed. So we cannot know beforehand how many buckets we will need. If initial number is too small and file grows very much, then performance will degrade because too many overflows will happen. If you have 10 buckets and thousands of records, then there will be overflows, and as many overflows are there, that many overflow buckets are there, that many chainings are there, that much more time it will take to search. So performance will degrade. Again, if you allocate too much space and the file doesn't grow significantly, then all that space is allocated and wasted, right? So one solution is that you can reorganize your file with a new hash function. Let's say every 3 months, you create a new hash function and maintain that uniform distribution, but that is an expensive solution. Better solution is that we allow the number of buckets to be flexible. That is, I can always take more buckets as I need. So I will not have a fixed number of buckets initially. I will start with however many buckets I currently require. If in the future I require more buckets, I can take more buckets. That is your dynamic or extendable hashing. Okay. Now dynamic hashing will take some time to discuss. So do you want to discuss it right now? Do you have a class after this from 6? I think you don't have a class, right? Because from 6, this class was supposed to happen.
Mad as it.
Okay. So I don't think I'll be able to finish dynamic hashing. It is very big. Okay, fine. I will discuss this in that revision session. But in previous term, again, I have the video for this. So check out that dynamic hashing video from previous term. In revision session only we discussed previous term also. What questions might come from this part, right? So I will discuss it once. For now, you can check that video. I will discuss in the revision session. But quickly, we have one more topic to cover, that is bitmap index. Okay, is static hashing clear for everyone?
Yes, ma'am.
Okay. We are going pretty fast today. That's why usually we have 2 classes for this. But see, week 10 is even more heavy on data, right? Much more content is there. So for week 10, we have to allocate 2 classes. We even have an extra class on Tuesday for that. So week 9, we had to have 1 session only. Okay, let's do bitmap index first. So till now, what have we seen? That every index has only one search key, right? Till now we have seen that. But I told you that index can have multiple search keys also. So when you want such an index where there are multiple search keys, that is called a bitmap index. So it is a special type of index which is designed for efficient querying on multiple keys. That is, you don't have to query on just the name or just the phone number. You can query on a combination of both. So records in a relation are assumed to be numbered sequentially from say 0. So instead of doing this theoretically, let me show you an example and explain. If this is my table, okay. What are the attributes? You can see ID, gender, income level, right? So now we will create a bitmap for gender also, for income level also. So how do we create a bitmap? First of all, a bitmap will have that many bits, as many as there are records in your table. So in this particular table, how many records are there?
5.
5 records are there. So if I want to create a bitmap for a particular attribute, let's say I want to create bitmap for gender attribute. How many bits will be in that bitmap? 5. So now which bits will be 1, which bits will be 0? That we can assign. So first tell me, what are the types of, how many unique types of values are there in gender attribute?
2.
2.
M and F, right? So I can assign, when I want to find bitmap for M in gender attribute, I want to find what is the bitmap for M, that is male. So I will turn those bits into 1, in which rows I have M. So see, this is row, first row, second row, third row, fourth row, fifth row. So in which rows do I have M? First row and fourth row. These two have the M values present, right? So when I create bitmap for N, the first bit and the fourth bit will become 1. Rest of them are 0. That means only these 2 bits or these 2 rows have M value present. Similarly, if I want to find for female, bitmap for female, in which rows female is present? Second row, third row and fifth row. So second bit, third bit and fifth bit, those are 1, rest are 0. Total number of bit represents number of rows, right? 5 rows, so 5 bits. So from this you can understand one thing, that bitmap index we only do for those attributes where there is a smaller number of unique values. If I do for ID, it is not required. Every ID is unique. That means in every case only 1 bit will be 1, right? If I want to find for ID 76766, which bit will be 1 in the 5 bits? Let's say I'm creating bitmap for ID attribute. Okay.
Only the first
So
will
for
be 1.
this particular,
Others all 0.
only the first will be 1, others all 0. Similarly for this one, only the second will be 1, others all 0. So we only create bitmap for those, that kind of an attribute where there are limited number of unique values present. Like in gender, only 2 unique values. Similarly in income level, how many unique values can you see in income level?
4.
4 different ones, L1, L2, L3, L4. So if I want to create bitmaps for income level, in L1, which bits will be 1? First bit and third bit?
First and third bit.
So first and third bit are 1, rest are 0. L2 is present only in second row, so only second bit is 1. L3 is present only in third row. L3 is present only in fifth row, so only last bit is 1. L4 is present in fourth row, so only the fourth bit is 1. L5 is such an income level which is there, but it is not present in any of the rows. That means if I tell you that there are 5 different income levels, but L5 is not given to anyone, that means L5 doesn't exist in this particular table. So all bits are 0. So for only those unique values which are existing, you will calculate that at which row is it present. Corresponding bit will become 1. Okay, now how do we solve numericals regarding this? What type of operations we can find on this? Simply, okay, let me take this example only. Here if I tell you, I want to find that how many people are there who are females with income level 2. Okay, I want to find the ID of the person who is a female with income level 2. Then first you find out what are the criteria. One is they have to be female. One is their income level has to be L2. So what is the bitmap for female? What is the bitmap? Tell me.
01101.
What is the bitmap for L2?
0 1 triple.
Okay. So what am I querying? That I want the ID of the person who is a female with income level L2, right? So now you do an AND operation of these two. Why AND? Because I want both together, right? I want female and L2. So if I do AND operation of bits 0 1 1 0 1 0 1 0 0 0, what is AND of 1 and 0?
0.
0 and 0 is also 0. 1 and 0 is again 0. Only 1 1 is 1 and 0 0 is 0. So now which bit is 1?
Second bit.
Second bit. That means which row? Second row. That is the particular ID we are looking for. Right. Similarly, if I say that I want to find out that for I want to find out the ID of male with income level L4. Then you will take the bitmap for male 10010 and L4. What is the bitmap? 00010. Okay. Then you do AND operation of these again. So only the fourth bit, that is the fourth row, this is the required ID. So this is how we can perform AND, or we can also perform OR operation. So if I say that either gender female or income level L2, then you do OR operation. Okay. Let's say if I do gender, I want to find the ID of people who have either gender is female or income level is L2. Then what do I do? What is female bitmap? Again 01101. What is L2 bitmap? 01000. Now we perform OR operation. So 1 and 0 OR operation gives what?
1.
0 and 0 gives 0.
0.
1 0 gives
1.
1. And 1 1 gives what?
1.
1 only in case of OR, right? And 0 0 gives
0.
0. So which bits are 1?
2, 3, and 5.
2, 3, and 5. So what is my condition? Either female or L2. So in the second row, bit number 2, row number 2. Female and L2, both are satisfying. So OR includes the AND also, right? OR is true even when both are true. Then bit 3 is 1. Row 3 is also there because female is there. L2 is not satisfied, but female is satisfied. Similarly, fifth bit is 1. So in fifth row also, female is satisfied, L2 is not satisfied. It's either or. So all 3 rows are coming as the answer. This is bitmap index. Okay, so there are some PYQs on bitmap index also, which we will discuss in the revision session. Currently, if I have one, I'll discuss. No, I don't have that right now. But okay, I will discuss that in the revision. But is the idea clear of bitmap index? What is a bitmap? Will you be able to form a bitmap yourself now if I give you another table and give you a particular attribute?
Yes, ma'am.
Yes.
Because you know what is the number of bits, number of rows in the table. And you have the unique values in a particular attribute. Like for gender attribute, 2 unique values, M and F. So 2 possible bitmaps. For income
Ma'am,
level,
what do we do with creating these bits? What is
this gives you the power to query on multiple attributes. Like I said, that I can query that what is the ID of in employees who are female having income level L2. So I am taking 2 different attributes into my query, both the gender and the income level, 2 search keys. But so far we had only seen 1 search key associated with each of the index, right? So bitmap index lets you query on multiple search keys. You can also take more than 2.
No, but suppose if there are say like 1,000, 10,000, or say 1 lakh rows.
See, that is the this thing constraint of bitmap, that we can only do it for such tables where there are limited number of unique values. Now, if this is a very big table, right, then this will be very difficult to perform. If for instead of gender, now if I take some name attribute, multiple people can have same names, or there can be unique names for everyone. So for that, the bitmap won't make sense. That's why I gave that ID example. For ID, only 1 bit will be 1 at a time because these are all unique values. So we usually form the bitmap on those attributes which have limited number of unique values, like gender. Okay.
Excuse me, ma'am.
Yeah.
Ma'am, in this bitmap, so if
Hmm.
is it always the first row represented by the left side, uh, rightmost side bit or leftmost side bit? Is it fixed?
No, it's not like that. See, bits are like this, right? 1, 2, 3, 4, 5, 5 rows. So similarly, 5 bits. So
Yeah,
left
but
hand side bit, you are considering it as the first bit, right? We
okay,
always
so
do that only. This is the MSB,
okay,
most
okay,
important, most significant bit. This one, left one. So you start from the left one.
okay, okay.
Okay, that is your first row. Then go
Hmm.
on like that.
Got it.
So dynamic hashing part is left, which is very important, but I don't have the time. So I will discuss this in revision session. Just one example. See this example that I have in this PDF only, this only we have to discuss. Okay. But this will take some time to understand. So we'll do it in either in one of the week 10 sessions or in the revision session. Meanwhile, you can check out the previous term revision session. There we have discussed. Okay, so a lot of information has been unloaded on you. If you have any doubt, please ask now, or you can ask on Discourse. Okay, or you can message me also. But I mean, for all of the topics that we discussed, is the basic idea clear to you? What is B3, B plus tree, how they are being implemented? Any doubt on that part? Just the basic idea of every topic we have done today. Anyone has a doubt? See, the important thing is if when you do a revision of this week, just go through this PDF. Okay, this contains all the important bits. Along with this, I will give you the formula sheet for that B3, B plus tree. Okay, I'll give you that sheet and we will discuss that sheet also in the revision session once. Okay, do you want this PDF? Do you want me to upload this today in Discourse? Okay, and I'm not uploading it yet because I'll also use the dynamic hashing. After that, I'll give it. Alrighty, that's it from my side, everyone. Thank you.
Ma'am,
If you
can
don't
you
have a
please
doubt,
upload it in supplementary content, ma'am?
supplementary. Okay, I have to give it to backend. Okay, fine. I'll
Thank
try
you.
to upload supplementary.
Excuse me, ma'am.
Yeah.
Yeah, ma'am, I just have a doubt regarding this OPE2 session schedule. Can I ask
Huh.
you?
Yeah.
Ma'am, is it possible to, prepone or postpone the schedule, our schedule?
The OP sessions, but OP is on 17th, right? So we have
Yeah,
to
I mean,
take in
on
next
17th, no, on 17th, the exam session I'm talking about.
the
Is it
exam
possible?
schedule.
Yeah, exam schedule. Is it possible to prepone or postpone?
I don't think so. You can ask support once, but I don't think they will change the dates. I mean, these are all scheduled before the term begins.
No, actually, I think only on Monday we got the mail about the schedule.
Yeah, you got the mail now, but the dates have been fixed beforehand. So I don't think they will change, but there is a reattempt also. If you cannot give the first exam, you can give the reattempt.
So reattempt will be on the same day or on different date?
Different day.
Okay,
But
so
still,
the
do
support,
one thing. You can just
yeah,
mail support once if you have a valid reason why you cannot give the exam on that date. Just mail them once and see what they say. Okay, if they give you a separate date, then you can give on that date.
okay, sure, ma'am, sure. Yeah, thank you, ma'am.